All right, well, the problems I've had you working on up to this point are you tended to build intuition that you can hold into what you understand about the labs and the rotational systems and all that stuff. Uh, I haven't gotten enough of that back to know how everybody's doing, but and some people have gotten me stuff, and yeah, what I've seen is pretty good. Haven't had a chance to get through it in detail. Hopefully, I'll get that done this afternoon or at the latest tomorrow. Something I've got to do with the heat of the house. It should just be a 15-minute job, but it might take me 3 weeks. Involves plumbing with gas, which is easier than plumbing with water, but nothing to it. The plumbing is plumbing. Okay. And that's kind of got to get done. I think it's done smoothly today, as it should. Then I should have plenty of time to get your feedback on what you got to me, and anything you get to me this afternoon. Okay. So I do apologize for being a little bit late on that. There were some glitches. Zoom acted up, and a couple other things acted up. Got them resolved, so we're okay. Okay, well, that's the end of my excuses. Okay, you've got your own. Understand? Okay, we're going to do gravitation. You're going to find it pretty simple, but conceptually, you might or might not have everything click. Okay, hopefully you will. Hopefully you've been thinking about these problems, whether you've been writing them out or not. Like I say, you need to think about them every day. That's how things sink in and become clear over time. You can't do it all at once. There's still time if you happen to do that, but get to the point where you need to use the time. Okay, you need to find the time. Okay, so bottom line. That's the start, but there's an arrow over this F graph, and there's no arrow over here yet. But I haven't completed the expression. Okay. Now, just out of curiosity, not to put anybody too much on the spot, but can you tell me how that fits in with what we've already done with the gravitation problem? All right. So what the thing that stands out here is it's an inverse square. Inverse square with R. What's R? It's a separation between two masses. You know, we had that little chunk of neutron star in here yesterday or Monday, and we have another smaller mass orbiting it, right? And that little chunk of a neutron star at a distance of a meter gave us a force of about equal to the gravitational pull of the Earth right here. Okay? Just the way the numbers work out. I didn't know they were going to work out like that when I did it in my head. And I did it on paper and I was right. So they did. Okay. So anyhow, you got this. All right. This is a vector force. Okay. So let's say we got the two masses. I think big M over here and little M over here. Okay. Which mass do you want to figure the force on? It doesn't matter, except that you're going to use an R vector. If you want to figure out the force on this mass, then your R vector goes like this. Okay. Now you're figuring out the force on little m uses the R vector that goes from big M to little m. And in this case, we multiply this force by the R vector over R. Now, R without the arrow over it means the magnitude of R, just the distance. The R vector has the same magnitude as this, but it has a direction. Okay? That makes sense? That's a unit vector then. Now, if you've had linear algebra, you know darn well what a unit vector is. Okay? You know, your orthonormal sets, dot, dot, dot. Okay? Divide the vector by the dot product, the vector with itself, square root of the dot product. Okay? All that stuff. So you want to, you know, it's been almost a year since you had a lot of that. And bring that in to your understanding of the physics. Okay? And understand that's a unit vector, doesn't change the magnitude of the force. Now, there's a problem with that. So if we calculate this, it's going to be a positive number because all the masses are positive. R squared is the square of the number that's positive in the first place, but it's positive. And big G is a constant, which is positive. Okay. So is that right? What direction would the force be in if we use this equation? Well, the problem is pretty obvious. If the R over R vector is in the direction of the R vector, is that the direction of the force that this thing is feels from this? No, gravity is always a force of attraction. Got it? If it was a force of repulsion, we wouldn't be sitting here. We'd be off in the ozone. Somebody in the ozone wouldn't even be there. Okay. Okay, so we put a negative sign in front of this so that now the thing points in the right direction. Okay. And that's it. And this big M times little m. Okay. Each of us is a little m, but big M is the Earth, right? And R is 634.8, whatever, kilometers, about 4,000 miles. Okay. And it depends. The Earth bulges a little bit at the equator, and we're a little further than sea level. So, you know, but we're a little M. Okay. And the Earth is a big M. Right? Okay. So the Earth pulls on us. And if we're here on the surface of planet, we're pulled back toward the center, not pushed away from the center. Okay. Magnets can give you attraction and repulsion. We've done a lot using magnets as sources of force in lab. And we've experienced both attraction and repulsion, pinch our fingers and everything. Okay. Gravity is only force of attraction, no repulsion. All right. So there's our rule. Okay. So now if we want to orbit, what little m to orbit big M? Okay, so it looks like we've got big M. And some circular orbit. Little m's out here and going around this. You know, at every point, the R vector goes from big M to little m, which means that the force goes in the direction opposite the R vector. So it's always a force of attraction. And circular orbit, as we've said, related to everything we did in lab and everything, centripetal force of the penny going around the path of the beam, well, its path on the end of the beam, and stuff we've demonstrated back there. At a certain point, speed the beam up, and centripetal force will be insufficient to hold the thing on, and it goes off. And at that point, we know what the force would have to be in order to have a circular orbit. Okay. Circular orbit gravity is a centrifugal force. Okay. Now, notice I didn't put vectors over these. And we don't really have to, because as soon as we understand that gravity is radial toward the center, right? It's centripetal, in other words. Okay. Then the centripetal force is also toward the center. They have to have the same magnitude. You don't have to worry about pluses and minuses. So this equals little m d squared over r. And I remind you, you really ought to know how to derive d squared over r. Simple picture, isosceles, triangles, and all that stuff. Yeah, I've done it. What does it? Well worth knowing so you understand it. But anyhow, we can solve this for v, right? Okay, well, just to keep you awake, go ahead and solve this for v. Very easy. Okay, I wasn't recording when I said that, but you know, we have the force of gravity equals centripetal force, condition for a circular orbit, because we need a centripetal force. Gravity is the only thing to give you a centripetal force if this thing's orbiting out there in a vacuum. So we set the expression for the force of gravity with force, set the expression for the centripetal force, solve for B. Very straightforward. We get B equals square root of G, big G, big M over R. Last question, what's omega? Okay, you think out through, you know, what's a radian? People are pretty conversant with the idea. If you think about a radian, I hope you're thinking about radian when you do this. Okay. A radian of angle is equal to a radius worth of arc distance, etc. You get omega equals V over R. Now, in the picture I drew here, if this orbit is in the XY plane, then what's the direction of omega? As I've drawn the picture. Okay, in the orbit, if the orbit's in the XY plane, then omega, well, by the right hand rule, is out of the board. If this is the XY plane, that's the K direction. If you have a right-handed coordinate system, and this thing's orbiting counterclockwise, K is positive. So we can put an arrow over this, put the K vector here. This means if some alien artificial intelligence decides to change the orientation, the plane in which the Earth-Moon system orbits, they're going to need a whole lot of torque. Okay? You know, just wave your hands and declare it, at least as far as we know. Okay. Maybe people just haven't learned to wave their hands right now. That's all. Okay. So that's pretty simple, right? What's the kinetic energy then? Write down the kinetic energy. Okay, now I see people writing down a delta KE instead of KE, which is pretty natural because we've done a lot of delta KEs. So if you're just thinking and trying to sort this out, that little delta under there is probably going to look okay to you, but it's not right. Okay, this is VKE. And what is VKE? Nobody has written down. Well, one person claims to, and I find this person to be at least 99.9% believable. Okay. The kinetic energy of the orbit is 1/2 mv squared, or 1/2 pi omega squared. Because if you wanted to use omega here, all I'd have to do is figure out a moment of inertia of this mass out there, which is mr squared. Okay. Kinetic energy of the orbit though is 1/2 mv squared, and you plug this in, and you get and see, I like to write a square on the arc, but usually when this is there, the r is squared, but this it's not in this case. Okay. And that's really straightforward. When I ask a question, the best way to start the answer for most people is going to be to write out 1/2 mv squared, because that's always what the kinetic energy is. You could also say it could be 1/2 I omega squared, where omega is just your mr squared for the mass here. Okay. Yeah, it's worth doing that. So I kind of recommend that you write that out if you haven't already. So it 1/2 I omega squared. There's your I. Here's your omega. Going to come out exactly the same. Okay, so that takes care of kinetic energy of any orbit. That's it. Okay. One little caution: if this is the moon and this is the Earth, then the center of mass, you're orbiting the center of mass, which is just a little bit inside the surface of the Earth, because you've got a factor. I think the mass of the moon is around 81 times, or the mass of the Earth is around 81 times the mass of the moon. So the center of mass between these things is 81 times closer to the Earth than it is to the moon. Okay, actually 80 times. But yeah. Okay. I think. Okay, I'm gonna concentrate on what I'm doing. Okay, so next thing is we talked about it last night. What's a potentially orbit relative to infinity? Because infinity is the only sort of universal point from which to calculate potential energies. Okay. If you come right down to it, it doesn't make a whole lot of sense to calculate the potential energy from anywhere else. You wanted to calculate the potential energy relative to the center of the Earth. Well, this says that the gravitational force becomes infinite as you approach the center of the Earth, approaches infinity. Center of the Earth is not a good place. Surface of the Earth wouldn't be terrible, okay, but it wouldn't be as convenient as you're going to see. And then you'd have to do a different potential energy calculation with the surfaces of different planets, stuff like that, and you wouldn't have a uniform point of reference. Okay. Okay, so your potential energy of the orbit relative to infinity. How do you get to potential energy? What's the definition of potential energy? Definition of potential energy in my course. You can express it as an integral, but the integral doesn't necessarily invoke anything except a bunch of symbols to students at this point. Typical student at this point just sees things, a bunch of symbols, and is developing an intuition. Okay. We want to develop as much intuition as we can before we mess with the symbols, which is why we've been talking about gravitation and orbits and so forth, relating to some circular motions we see in the lab and answering questions that precede this symbolic development, okay? So we have an idea, and I'm not saying you're terrible people if you haven't done all that. Okay, I mean, we're all terrible people, just take that, right? Yeah, but seriously, we're all okay, but to be okayer, we try to hold the intuition with the symbol, okay? And the definition I've given, universal definition, because you can give me, you think potential energy is MGH. Well, I say bull feathers, okay? Unless you can tell me why it's MGH. And the conditions under which it's MGH, which condition is H is parallel to a uniform gravitational field, which we certainly don't have here. So please promise me you're not going to try to use MGH for this. Please promise me that you will understand as best you can when MGH applies and when it doesn't. I have people second semester still trying to apply MGH to the force between two protons. Okay? I hate that formula, which is why I usually write it mg delta y. But I talk about why it's so, because this is equal and opposite to the work done by gravity. That's the first thing you heard me say about potential energy in this course. Okay? So, I say, that's the first definition. It's not a completely rigorous definition because you could ask, well, work done on what? Okay? Well, it's the work done on the thing you're trying to find the potential energy of. So I regard that as implicit. We start thinking about potential energy by this, because otherwise it's really easy to get screwed up and mixed around. Okay? And you're going to see that as we work out the potential energy of this mass relative to infinity. Okay. So you got a mass here. All you know about its position is at some distance r. Another mass, which exerts a gravitational force on it, therefore does work as this thing moves. Okay. Now, as this thing moves away, let's just pretend it's on a straight line from here. In multivariable calculus, you'll learn that it doesn't matter whether it's a straight line or not, because you'll learn what a conservative force is. Okay. Right now, I'll just say, if it moves from this distance to this distance, doesn't matter if it goes from here to here, or from here to here at the same distance, or from here to here, okay? Anywhere, the distance is the only thing that determines its potential energy, okay? So here's the situation. We want to figure the potential energy of this in the gravitational field of this mass. Think of the Earth in the moon or satellite, preferably satellite that will blast off to Mars or something. Okay. And incidentally, Mars is pretty close to infinitely far away as far as energy is concerned. Really close, actually. So what do you do? For our sake, you're going to continue, you're going to consider the work along a path that continues along the radial line. Okay. Now, if we take an increment delta r along this path, okay, and we let, okay, let me back up just a sec. I've used R for the orbital radius, okay? Since my gravitational force depends on R is going to have to be variable as we go here out to infinity, right? So we don't want to use the same letter for this specific radius as we do for the variable distance, okay? So I'm going to change this to A. Okay. Orbital distance A. Then, what's my gravitational force out here? Well, that depends on how far I am from the big mass, right? The center of the big mass. Okay, so along this line, R varies A to infinity. At this point, some point within here, okay, I'm going to just wiggle my finger back and forth between one end of this interval and the other, and somebody tell me when to stop. Just raise your hand to tell me to stop. Okay, so I was right here. This is as good a point as any. I'm going to use a little asterisk to mark the point and say R equals R asterisk at this point. Okay. So the gravitational force do the vector. So what's the gravitational force at this point? No, there it is. Okay. It's negative G big M little m over R squared times G vector R vector divided by R. Except now, this is at what? This is at R star. So the R star vector goes from here to this point. We're just calculating the force of gravity at some point in this little interval. Now this should be familiar to you. Probably presented a little differently than it was in calculus 2, or maybe even calculus 1, depending when you have the first definition of an integral. But we're just going to follow room on some here. Okay, so this is a sample point. Did you use that terminology in calculus, sample point? Okay. You certainly did if you're in my motor variable calculus, but I'm talking about calculus 2. Pretty standard. But I don't know for sure. I haven't investigated the text. Okay. But I'm going to call this a sample point within the interval. It didn't matter where you told me to stop my finger. Anywhere in this interval is going to be okay, because ultimately we're going to do the sum of all these intervals, and they're all going to shrink to size 0. So there's less and less wiggle room for where this point is. So as we take our limits, as the size of the interval approaches 0, we're going to squeeze this R star down to a point, and everything will become exact. Okay, anyhow, there it is. Okay, now how much work is done? Well, delta R is also a vector. This arrow was originally indicating how long this interval is. It's also over the delta R, so we're going to give it 2 purposes. Okay, tells us how long the interval is, and also tells us that delta R is a vector. So now, what's the work. Now I'll use delta W for the work done by gravity on this interval. Okay? It's the contribution of the work done by gravity. Now, what's your definition of the work done by a vector force over a vector displacement? Okay, now let me comment. I asked for the work done by a vector force and a vector displacement, right? Okay, and then kind of came up finally with cross product. Well, couldn't be cross product because work is a scalar. You don't say I do 50 joules of work in that direction. You might say I do 50 joules of work while something is moving along a path that goes from here to there, but work doesn't have a direction. It's just a magnitude. It tells me how much energy I'm sucking out of my battery or how much glycogen is being converted to energy so I can do the work or whatever. And if it's glycogen, I don't know physiology. Okay. I should look that up. Just ask pretty much any member of my family who knows these things. Okay. Work done by gravity is the dot product of the force and the displacement. Well, what's the dot product of this with this? Well, it's G big M little m R asterisk squared times R asterisk over R asterisk. Okay. This being a unit vector dotted with delta R is the magnitude of this vector. Okay. But it's in the same direction as the radial line, right? The direction of this is the same as the direction of the radial line. You can puzzle over that a little bit if you wish. But the dot product of R star over R star, vector R star over R star, dot product of this unit vector and this unit vector, since they're in the same direction, is just one. That tells us that we got big G, big M, little m over R squared, just times delta R, except I didn't use the right expression here. The force is negative big G, big M, little m over omega. So that's one opportunity to screw up a negative sign. We don't want to screw up negative signs. So it's so easy to do. Okay, so now we know that work done by gravity is this. Okay, well, now we chop up this interval into as many subintervals as we like. Make these delta R intervals as small as we like, and we just add up these expressions. Well, I say we partition Rotation the interval from R equals A to R equals B into small intervals. Now, I'm not going to be completely mathematically rigorous about this because this is never R. Okay? Actually, I have sometimes this figure out. So you certainly know a lot of that. Okay? So what I get is work from A to B is the sum of, let me, partition is A equals R naught, which is less than R1, dot, 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 up to R sub I minus 1 and R sub I, and then dot, 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 up to R sub N. And I should write that more carefully. So I've got a bunch of positions along this line that run from A to B. Now, why don't I go from A to infinity? You don't want to have a finite number of intervals, that's why. Okay. There's your partition. Now, on the partition, it's now going to be a sum of delta W sub i's. I could have called this a delta R sub I, and I could have called this an R star sub I. Okay. So I'm kind of glossing over that in a way that should be obvious. You're going to get this sum. Okay. And it's not from I equals 1 to infinity, it's from I equals 1 to N. This approaches as the width of the intervals approach 0. The integral from A to B. Why from A to B? Because that's what we partition. Partition the interval from A to B. This works for any finite distance we might want to go. Okay. From an orbit at a height of 300 kilometers, an orbit at a height of 500 kilometers. A would be 300 kilometers, B would be 500 kilometers. From here to the moon. And then maybe even just from the surface of the Earth to the moon. Potential energy change. A would be 4,000 miles roughly. Moon would be 250,000 miles roughly. Okay, change that to meters if you like. So this works for any distance. And this delta R I over R I squared becomes a dr over R squared by some magic that physicists usually wave their fingers over, but mathematicians understand, and so should physicists. They just don't want to take the time to do something obvious. Okay, so kind of wave their fingers, but they know how to do the stuff. So this approaches this interval. which is what? Well, let me fix something, because I keep neglecting to put my negative sign on this. Negative sign comes from the fact that this is a force of attraction. Right there it is in our definition of the force. So I have to have a negative sign in front of this, a negative sign in front of this, and a negative sign in front of this. So here's my arrow approaches negative big G, big M, little m over d r squared. Well, that equals what? That equals positive G m, little m, over r, evaluated from A to B, equals big G, big M, little m, over B, minus big G, big M, little m, over A. Now, what happened to my negative sign here? Well, when I integrate 1 over r squared, I get negative 1 over r. So that r came from, right? You should fill in the details in this integration. You should understand this. It's not difficult, except to keep track of the signs and then to interpret. Okay? That's not difficult to interpret if you understand details of the integration. So work from A to B. Equals okay. Now, how do we get the work from 0 to infinity? Well, you would maybe want to say replace B with infinity, so then you just get big G, big M, little m times negative 1 over A. Well, B is a number, infinity isn't a number. So to be formal about this, and you really need to be able to be. Work A to infinity is limit as B approaches infinity of the work from A to B equals the limit as B approaches infinity of big G, big M, little m times 1 over B minus 1 over A. And then by theory of limits and so forth, you know that the limit is B goes to not 0, it's infinity. Okay, as B goes to infinity, 1 over B does go to 0. You can prove that using stuff you learned in the first week or two of the calculus class. And you should review that. You want to be aware of that stuff. It can pop up its ugly head at any point in an engineering curriculum. Okay. Not only, even if you don't have to formally do it on a test or on a homework or something, if you understand it and understand what it's telling you, then you understand how to do a moment of inertia. You understand how to do gravitational potential. You understand how to do an electrostatic potential. You understand how to do all kinds of important things. So that maybe you know sure what integral to put into the machine, or how to develop the integral you need to put into the machine. Okay, these things are important. So that kind of advocate. And this then equals big G, big M, little m over A, except you got that negative 1 over A, so it's negative. This is the potential energy at distance A relative to infinity. Now, I just got a question from somebody saying, well, should that be positive because this is negative or whatever? No, keep track of your negative signs. Like I'm inclined not to, but I always go back and fix them. Make sure I've done my negative signs correctly. I have a negative here. I don't have a negative here. Why not? Because I integrated 1 over r squared, which gave me negative 1 over r. So that now a reciprocal r squared becomes a negative reciprocal r, which takes care of that negative sign. And then, yeah, value at B minus value at A gives you this. That's the work done by gravity. That's the work done by the conservative force. Okay, in this case. And when I gave this definition, I said gravity and that's not definition, that's a definition defined of gravity. By conservative force being one that's path independent. Okay, so if you move your path backwards, you get back to zero. Okay, well, there it is. Now I was going to first place, I define the work that we're talking about as the work done by the conservative force, which is a gravitational force dotted with the displacement. Okay. So everything here is a rigorous development. Unless I'm saying it completely wrong, which is always possible. But I don't think so in this case. Prove me wrong. One of us learns. Probably both of us. Okay. But this is totally consistent with what it has to do. So let me ask you this. Okay. What has a higher potential? Something that's closer to the center of the planet or something that's further? And by a higher potential energy here or here. Okay. Now I ask you, are you higher or lower potential here than you'd be out here somewhere? If you move further away, you get at a higher, do you have a higher potential energy or a lower potential energy? And people want to say, well, it's higher. I mean, it's lower because the bigger A is, the less big G, big M, little m is, right? So big A means a small, big G, big M, little m over A, right? And small a means a big one, but it's got a negative sign in front of it, which means if A is small, you got a big negative number. If A gets bigger, you have a smaller negative number, a negative number that's closer to zero. Okay. So we can kind of do the picture. I never know what answer I'm going to get, so never know exactly how I have these boards lined up. Okay, so this means if my big M is here, then which orbit has the higher potential energy? Now you do have your intuition that goes back to raising the concrete block and dropping it on my foot. Okay. Unfortunately, I only wear steel toe boots, so I can get away with that, but I don't really do it all stuff up the shoes. Okay. Higher potential energy, release it, lose potential energy, gain kinetic energy. That's your first example. Clearly then, if I lift something from here to here, my potential energy should go up. But this big G, add up G, it's even worse, there it is. Big G, big M, little m over A is smaller here, bigger here than it is here, because A is smaller, right? A is small, and this is big quotient. If A is big, this is a lesser quotient. So big G, big M, little m over A is clearly less here than it is here. But when you put that negative sign in front of it, it's like on a number line. Here's 0. Here's big G, big M, little m over A. Call that A1. Here's big G, big M, little m over A2. And the active potential energy is over here. It's negative big G, big M, little m over A2. And negative big G, big M, little m over A1. Okay. So if A1 is bigger than A2, yeah, this is bigger than this, but this is greater than this. This is still, in a sense, bigger than this, but it's negative, so greater means to the right on the number line, right? And you can think then of concentric circles going out all the way toward infinity. As they go toward infinity, this A1 approaches infinity, so the denominator approaches 0. So these numbers here, your actual potential energy, approaches 0 as A1 approaches infinity. Does that make sense? I recommend that picture because it can get very hard to keep track of this. It's kind of counterintuitive. And especially second semester when this becomes even more important, okay? Make sense? Because if you use the Bohr atom of the Bohr model of the atom, you can think of orbitals and angular momentum, okay, and potential energies and kinetic energies, okay? It's not really what happens, it's quantum mechanical. The basic model is kind of what I said. It's like a planetary model. It happens to work really well. But when you get into really tight observations, you realize you really got to go to a much deeper, more sophisticated model that's based on linear algebra that you haven't imagined yet, and multivariable calculus on steroids. Okay? Now, if you're not going to be an atomic physicist, that's just kind of think of the Bohr model. You get away with it. All right. So anyhow, you get the potential energy picture for orbits. Well, now what do we know about the energy of an orbit? Okay, well, we already said, let's summarize this. This is for a circular orbit. If distance r is u plus k, potential energy plus kinetic energy, right? Equals what? U is this. At distance a, it's negative big G, big M, little m over a. Well, now we'll say if distance r, so we're going to replace a by r. So we used a because we wanted to use r for our variable of integration. Now we're done with the integration. We've got the expression. It's negative big G, big M, little m over a plus 1/2 big G, big M, little m over a, because we got that right here. Okay. And this equals negative 1/2 big G, big M, little m over a. Over. And I just used a when I said I was going to use r. Because now I'm using r for the radius of the orbit. Okay. Now, circular orbit at R2 versus a circular orbit at R1. And let me change a couple of these words here. I want to do this in a direction. So circular orbit, I'm going to go from R1 to R2. Okay. Which one of these is bigger? That depends on whether R1 is bigger or R2. Maybe you want to go from an orbit out here back to an orbit here, or from an orbit here out to an orbit here, right? So if we assume that R2 is bigger than R1, this negative number is going to be closer to zero than this negative number, right? Now you might want to think through this. That tells you that you're going from a more negative number to a less negative number. You're going like from here to here. Okay? Which means your total energy has to increase. Of course, your total energy has to increase, but here's your kinetic energy. What's your kinetic energy? If R2 is bigger than R1, your kinetic energy decreases. But your potential energy being negative over R increases. And it increases by twice as much as your kinetic energy decreases, which means you're going to have to use your rocket engines. Okay? And then you can think, what happens if you want to go from R2 to R1? Okay? Your total mechanical energy is going to increase. Okay? And your speed doesn't increase enough to use it all up. Your potential energy is going to change by twice as much as your kinetic energy does. Your total energy is going to go lower. So you got to expand the difference in energies. Okay? So work that out. Think about that. There's your framework. And all we're going to talk about here is circular orbits with a little bit more hand waving on elliptical orbits. If you understand what happens in circular orbits, first place, the mathematics of elliptical orbits is tougher. And people don't usually come into the course with kind of preparation and polar coordinates and parametric equations that they're supposed to have. And we kind of attribute that to COVID these days. But it gets covered, I think, in most courses up to this point, but not to the extent that anybody remembers it very well and can use it. So we're not going to attempt to do elliptical orbits. Okay, but we'll talk about them. And we've already talked about the fact that the angular momentum doesn't change. Angular momentum doesn't change because the force is always toward the planet. So it has no moment arm. It exerts no torque. Can't change the angular momentum if you don't exert a torque. All right, now I'm going to sketch out simple harmonic motion real quickly. And then we'll talk more about that. Okay, now the problems I ask you to work on and hope that you can work on, or hopefully you've done some work on if you haven't completed them. I ask you to lay the foundation for understanding what I'm going to tell you. But your net force, you multiply your net force by your displacement. I said you can easily average the net force between 0 and x, which is going to be 1/2 of the negative kx, right? Then you say, okay, if I move from here to there, how much work do I do? Okay. Okay. Simple integral, we've done it. See, this is the work done by the conservative force. Okay. So maybe I'll put a CONS. Attach my subscript. Okay. There's the work. Potential energy is equal opposite to the work done by the conservative force. This is the work by the conservative force. This is a change in kinetic. But I looked up the potential energy. You know, just change the signs. Using the fact, change the potential energy is equal opposite to the work done by the conservative force, which you really ought to drill into your head for the final exam. It's going to come up multiple times. Not in every problem. Could I could throw it in every problem. Don't want to beat it to death. I want to give you a fairly balanced test. Okay. So if you don't know this, it shouldn't kill your grade. It should just damage it. Okay. Okay, so that's it. That's potential energy. Okay. Well, we could also say the conservative force is negative du dx. We could have done that with the gravitation. Okay, we have well, I mean, you got this is where we started. Okay. Didn't do the vector form here because we understand the gravitational model. After we've derived everything, we don't necessarily need the vectors at every stage. And we're not really talking vectors here, but these are vectors. Okay. And this would be your f dot dx. There's your f, you dot it with dx, which is in the same direction. So anyhow, what do you get if you take the derivative of this? You get kx. It's negative, so it's negative kx. That's full circle. Okay. What else do you know? You know that MA equals negative kx. So A equals negative kx over M. So X double prime equals negative K over M. X. So X equals A cosine of omega t plus 5. Omega equals negative K over M. Now you should be able to do that in your head 3 times as fast as I did it, writing it out. You need to know this. You need to know this to understand what's going on in simple harmonic motion. Once you do, then in a condensed situation for simple harmonic motion, you can easily identify A and omega, and if necessary, phi. Just a matter of doing a little substitution in a simple trigonometric function, okay? Then to identify omega, since omega is the square root of k on ground. At the stage where if I write a symbol, it must be the one I meant. Okay. How do you get K? Well, that's your force constant. Remember measuring the force in that rubber band over there? Got that data? Hope so. Somebody wants to email me their data. If I get at least a couple of forms of that data, I can disseminate them because they're probably going to need it for a couple of questions I'm going to ask it over the weekend. Not everybody might have measured it. I think everybody did. This is kind of important. We haven't used it too much since then, but we're going to do it Monday. Okay. Actually, we're going to do it Friday. We have lab this week. Planning on it? Okay, you want to do it the last day of class? Okay, that's fine. So we'll do it Monday. If you're not here, check out the video. I'll try to get everything on the video because I know some people are traveling for Thanksgiving. Okay, again, the whole thing is here. There's your equation of motion. How are you going to get your velocity? You got to take the derivative of that. How are you going to get your acceleration? You're going to take the derivative of that. How can you figure the velocity at a point if you release it from some known distance? You're going to find the change in kinetic energy and solve for 1/2 mv squared equals change in kinetic energy change 1/2 mv squared. Okay, that's really simple conceptually. The details, like always, that's where the devil be. Okay, it's not that bad of a devil if you practice it.